Hello, everybody. So again, my talk is Rustling Out Predictive Sports Betting Models on the Beam. Usually you only hear about projects that go well. And all the twists and turns in between are forgotten. So today I'm going to tell you a different story. One about how we use NIFs to deploy machine learning models on the Beam using Rust. And I want to tell you about how that ended up being successful, but why we chose to move away from it. There we go. Okay, so hello, I'm David Lucia. I love Elixir and contributing to open source projects in the community. I'm very proud that I had my first Erlang contribution this year. I was at CodeBeam last year and had a lot of fun, met some friends. Hi, Igor. And I hope you like my talk. Okay, so today's topics, I want to introduce you to sports betting. We're going to talk a little bit about machine learning on the Beam and how we built one really big NIF. And I want to get into organizational design and how a lot of the technology choices that we made were impacted by the way that our organization was shaped. Okay, so first I want to start with why. So a year ago or so, I joined SimpleBet. We got a lot more people coming in. Hello. And I came into the sports betting world not knowing a lot about sports betting. And it turns out that the sports betting industry is very old, but is really starting to open up right now. And there's a lot of change that's currently happening. So a reason for this change is that a federal law was overturned called PASPA in May of 2018, led by everyone's favorite governor in New Jersey, Chris Christie. It opened up sports betting to the United States, so now individual states can draft legislation to make sports betting legal in their state. So now states like New Jersey, Nevada, Montana, they're all opening up to individually have laws to allow sports betting. So if you live in one of those states, you probably get a ton of ads for like FanDuel or DraftKings, these daily fantasy sports companies that are now moving into the sports betting space. And so what's different now is that the industry has really sort of lived in Europe and Asia and hasn't really existed so much in the United States. And in the United States, we're interested in sports like NFL, the NBA, MLB, but also the US consumer is kind of, the Instagram culture of instant gratification. So we have like a new type of consumer that we're dealing with as well. Okay, so to get everyone on the same page, some terminology. What is a market? A market is something that you could bet on. So the Yankees, Red Sox money line. A bet or a wager is taking a stance on one side of the market and putting money down on it. A stake. Stake is just how much money. Selections are your options for that market, like what can I bet on? So if you've heard of an over and under, you could bet on the over or the under. Those are your selections. Odds are your payout, so if you're going to 2x your money, those are your odds. And then a sports book is a company that accepts bets and wagers. So example of a sports book would be like FanDuel or DraftKings in the United States. Okay, so how do odds get set right now? So you might have heard of like, the Vegas line. And for big games, for money lines, the way that this works is there's some guy in a casino somewhere in Vegas, and their job is to set the odds. So they're looking at other bookmakers, and they're adjusting their odds based on how bets are coming in, and trying to make it so that the house wins money. This is mostly gut-driven and not really a science, more of an art, I would say. Okay, then there's other types of companies that use simulations. So for example, soccer, when you're betting on outcomes that can last the entirety of the match, they'll use a Monte Carlo simulation. And for each iteration of the simulation, they'll count some statistics, and then they'll run that 10 to 100,000 times. They'll divide that by the number of simulation runs, and now you have the probability of that statistic happening, and they can use that to drive the odds of the market. My director of machine learning systems, when I asked him to review my slides for me, yelled at me for using game of life to represent a simulation. So sorry if you're a mathematician. Okay, and then there's the third approach, not the only, these aren't the only three ways of generating odds, but another approach is the machine learning approach. And this is where you design a model using features and you're trying to capture nuances of the sport. You then take that model, you run it against historical data, and then you run that, and then you have this model with the tuned parameters from running on the historical data, and you use that to predict on future data. So this is really good for predicting odds that have a number of factors going into it, but not for really long running things that you're trying to simulate that would regress to the mean over time. All right, so I want to give you just a little bit of an idea of kind of the industry standard for what's out there right now in terms of what you can bet on. So the simple one is the money line. Is Team A going to win or is Team B going to win? Pretty straightforward. Then you have your spread markets, which is Team A going to beat Team B by some number of points? The over-under, this is where the line comes in, and the dude in Vegas is like, all right, well, Team A and Team B, let's imagine this is baseball, so are both teams total going to score more than 8.5 points or under 8.5 points? And 8.5 is the line, and it's set at half so you can't tie. All right, so this is all foundational knowledge. I want to explain how odds work and how they're set. So we're talking about the money line again, Team A versus Team B, who wins? The implied odds, or the raw probability, is that there's a 40% chance that Team A will win and a 60% chance that Team B will win. Adds up to 100%. The decimal odds are just 1 over that probability, so 2.5, so that's a 2.5 payout for if you win on Team A, and 1.667 for Team B. And then the American odds, we like to make things complicated, imperial system. So the way that the American odds work, the positive number is the underdog, and that means that if I bet $100, I'll win $150. The negative is the favorite, and that's if I bet $150, I'll win $100. I don't know who invented that, but I'm kind of angry at them. Okay, and so unfortunately that last side was too good to be true. Kenny Powers got to make money, so do sports books. When you bet, you don't get favorable odds. The house puts some margin on top. Sportsbook adjusts the odds for the desired VIG they're looking for. VIG is a kind of fancy way of, it's kind of like a metric for profit. So in this case, that 40 and 60% that adds up to 100%, we're taking a 10% over round, which is 10% over 100, over round, get it? So distributed evenly, 45 and 65, now we're at 110%. If you do the same math, you get these slightly worse odds and you make slightly less money if you win. The VIG is calculated by the over round over 1 plus the over round, I think. Let me look. Yes. So just a metric. You might hear VIG if you were ever around people who bet on sports. That's what that means. Why isn't this working? Okay. So here comes SimpleBet. SimpleBet is the company that I work for. So SimpleBet makes in-play discrete occurrence markets possible by combining machine learning and automation. So this app on the right is an app that we built last year and released as a beta to closed audience for the playoffs and the World Series. So we want to make it so that you could bet while the game is happening. And we want you to know within minutes or seconds of placing a bet if you won or not. So again, Instagram culture, instant gratification, US market playing into that. So we started out as a company because our founder thought that, those American odds that you saw, it wasn't very approachable for someone who's not, a hardcore bettor, more of a casual sports fan. He wanted to tailor to that audience. And so we wanted to build a more intuitive and engaging experience for that casual fan. So the example you just saw, we call it plate appearance exact. So you could bet, in this case, Buster Posey is going to hit a home run on this next at bat. We're going to place $5. You'd win 111. How many pitches are going to be in this at bat? So I bet that in total, before the at bat ends, there's going to be 5 pitches exactly. Making it a little bit faster, so now we're talking about 20 to 30 seconds of time. You could bet on, is the next pitch going to be a ball, a strike, or in play? And looking a little bit forward, right now we're focused on baseball, but what is the result of the next drive? I think it's going to be a touchdown, and I'm going to get 4 times my money for it. Okay, so we started by wanting to make this user experience better, more engaging. But when we went to do so, we realized that the reason why this doesn't exist is not because you can't make this engaging UI, it's that those odds don't exist. And you can't have, you can, just very expensive to have a lot of dudes in Vegas setting these odds as the game's happening. And that simulation approach that I talked about doesn't really work because it's not going to be as accurate enough and you get beat all the time. So what we do is we ingest from different data sources and we offer these odds as a service for other sports books. All right, so let's start talking about machine learning on the beam. Now, in order to offer those markets, we need 2 different types of data. So down here are historical data. For the MLB, you don't need a year, you don't need 2 years, you need like 10 or more years of data. And so we have all of that data ingested. But then in order to know what's happening live while the game is progressing, we have to ingest from live data sources. So there are companies that resell data on behalf of the league, and we pay them handsomely to send us data, incremental information about what's happening in the game. And we need to reconstruct that to know who's on base, who's the current pitcher batter, anything you might need to capture to package it up and send it into a model. That model will then do its thing, and output a probability distribution. And we use that probability distribution to set all those odds so that you can have that fun app. Now, the challenges here is that coordinating data from all these different sources, if you have live data, it might not just come from one source. You might need to have, depending on the granularity of the data, you might need to get it from multiple different places and aggregate them together. You also want to make sure that if there's, the referee comes in and, blocks the pitch, or I don't know, something crazy happens in the game and our logic can't handle it. You don't want one game breaking to affect another. And we also need to make sure that the predictions are fast enough so that they are viable. If you have a 20 to 30 second pitch market, the time to get that out is very narrow because we send it to the sports book and then they send it to the customer and they still need enough time to bet. So when we first set out to do this is how our team was set up. So we had a data science research team who's working in Python. We had this machine learning engineering team. So the data science team would build models, these machine learning models. They design them, they test them, they make sure that they're perfect, and then they'd throw it over the wall, and we'd catch them. That'd be me. And I'd be here in the machine learning engineering team building these models in production in Rust, and then shipping them off as a NIF into our platform that's all written in Elixir. So this data science team, math and statistics background, lots of PhDs. They're focused on modeling and feature engineering, trying to build the best model possible. They have enough software expertise to get dangerous, but haven't designed in-depth distributed systems in the past. And then we have our machine learning engineering team, which is a bunch of low-level systems programmers. Pretty much no machine learning experience, but Rust is cool and we can't wait to use it. And then we have this platform team that's kind of consuming the model, doing all the coordination. These are people coming from Java, Scala, Node, some Elixir, led by a team that has a lot of experience with Akka and the Scala ecosystem. And like I said, they're responsible for the coordination. So it's not just about pricing the markets. We need to create them, price them, and then when we ultimately know the result of the market, result it and send that out as well. So why use Elixir for this? I'm talking to a room of Beamers, so you'd probably know by now. Elixir is a perfect fit for this coordination problem. The multiple games thing is, it fits into a process model very nicely. With supervision, a lot of the problems that I described with one game affecting the other, Elixir can handle that very well. Now, on the Rust side of things, that's where it gets a little bit more interesting. So Rust, there's not a ton of tooling that exists in the Rust ecosystem for machine learning. And so we knew that we can combine Elixir and Rust and deploy them as a NIF. And excuse me. If we can deploy our models as Rust code, we knew that we could ship them as a NIF and get them out into production. Very easy. So this is what we ended up calling the dream stack. And this kind of started as a joke, but then I said it publicly, and then other people started asking me about the dream stack. So before we get into all of that, let me describe what a NIF is. So show of hands, who has written a NIF before? Okay, so a surprising number of people. I see Igor is not sure. All right, so for those who don't know, a NIF is a simpler and more efficient way of calling C code than using port drivers, of course. NIFs are more suitable for synchronous functions that do some relatively short calculations without side effects and return the result. Thank you, Erlang documentation. So NIFs were introduced in 2009, so about 7 years before I started using the Beam ecosystem. And it allows you to call native code from Erlang as if it was a normal Elixir Erlang function. They can accept and receive Elixir data types, and they can even keep state. Now you should use NIFs, I think, for only these two cases. Maybe you can convince me of others. So when you need to interface with something native, so for example, libsodium is a crypto package that is a lot more fleshed out than the crypto package in Erlang. Floki is an HTML5 parser from the Servo Mozilla project. There's other HTML5 parsers out there, but maybe you can argue that you need that one. Sass compiler, I used this while I was at the outline to do dynamic story templating. It was cool. And then the other use case is speed. So I've got some problem and I can't squeeze enough out of Elixir and Erlang, so I want to go native. So sorted set, there's a data structure, NIFC, faster file system manipulation, no way Jose, JWT signing. So my favorite example of a NIF, Discord has a great blog, and they wrote about how they had this problem of needing to sort hundreds of thousands of users super quickly, and they tried to optimize their data structures in Elixir, couldn't squeeze out the performance that they were looking for. They used a NIF and that sorted set data structure I talked about, and it worked perfectly for them. So probably can't see this from all the way in the back. This is directly from the Erlang documentation, and this is an example of a NIF. We're going to go through a more in-depth example in a second. But basically, on the left, you have an Erlang module. It's exporting 2 functions, and if you call those functions, it would throw NIF library not loaded. But the caveat is that there's an onload callback, and that onload callback calls the NIF, which is a all C code on the right. And as long as you're using the right header and the right C macros, it will swap out the Erlang implementation right there with the C implementation. So the way that NIFs are compiled is as shared objects. So if you've ever done any C programming, you call GCC with your main function, and then you run the executable. Shared objects are like executables, but with no main function. And basically what happens is the linker, it pulls it into your program. The way that things get connected together, the puzzle piece, are the header files. And in our case, erlnif.h is the thing that pulls them together. So NIFs are very powerful, and there's a lot of really cool things, as I noted, that you could do with them. There's just one minor problem. Crashing in Elixir and Erlang is fine. The beam is built for that. Let it crash. C does not play by the same rules. So in this case, don't let it crash. And don't have a bad time like that kid. So if your C program, your NIF does crash, it's going to take down the whole beam with it. And obviously, that's undesirable. So enter Rustler. Rustler was originally built by Hans Elias J. I believe he works at Dockyard right now. I think he's working on the Lumen project, though. Rustler makes it easy to build Rust NIFs and link them into Elixir code. So Rust is a systems-level programming language, originally coming out of Mozilla Labs, but now well supported by the community. I'm technically part of the Rustler core team. I don't have the capacity to contribute, but very nice of them for them to have me. Okay, so what are Rustler's goals? The goals are safety, interop, type composition, and resource objects. So safety means that if I write code in Rust, it should never crash the beam if it's deployed as a NIF. Interop, I should be able to transfer data in between Rust and Elixir in its native type very easily. So Erlang terms on the Elixir Erlang side, Rust values on the Rust side. Type composition, so if I want to make something encodable or decodable on the Rust side, it should just be a quick annotation rather than writing a ton of code. And then resource objects, where it makes it really easy to keep state inside of a Rust NIF. And we'll get into it in a second. Okay, so we're going to build our first model in Elixir and Rust, and model in quotes because it's not a model at all. So if you want to follow along, that is the URL, DavyDog187. It's my 5th grade screen name still. /baseball. Okay, so can anyone in the back see that? Probably not. Sorry. So basically, when you're starting a Rustler project, you call mix Rustler new. You tell it the module that you want to inject into, generate some boilerplate for you in Rust. You need to hook it into the module with a use macro. So you use Rustler, you say the name of the OTP app, you say crate with the name, and that crate is the Rust word for library. And here I have 4 functions that I'm stubbing out. If they're called directly if I took that use Rustler away, they'd all throw an error. And so the idea is that use Rustler, it's going to do that onload callback that we saw in C, and it will swap it out with the Rust implementation when the module loads. So this API that we're building that's trying to model it's modeling a model. It's modeling our baseball predict function. So there's 4 functions. There's prepare. So we want to take a bunch of data, historical data, and we want to store it ahead of time for use by the model. So that's going to store the static data inside the NIF as a resource object so that we don't have to keep passing it into the NIF. You do it once, it stays in that memory. Then we're going to implement update, which updates the state of the game. So Simple example, you pass atom home score, atom away score. It will update the state inside the NIF. Get scores will pull out the current score, and then predict will run the model. Okay, so this is a test to illustrate the flow here. So I just have a list of floats, and that's my fake data. I'm going to call prepare, and prepare will, passing those numbers will give me back OK with a reference. So it's not a reference to any data, it's a reference, and this actually points to that memory location that's holding all that data in the Rust NIF. Now I call baseball.update home score, away score, home score, home score. So at the end of that, I should get 3-1 back. And notice that each time it's returning OK. So similar to how I could send a message to a gen server and it could keep updating state, it's the same concept. I'm not getting any of the state back and repassing it. It's not functional. It's mutating inside. And then at the end, we call predict. Okay, so once we call mix Rustler new, it's going to generate some boilerplate. This boilerplate, doing OK on time. The first thing you need to do is you need to say, these are the names of the functions with their arity that I'm exporting and a reference to the actual Rust function. We're also mentioning the module up here in Rustler export NIFs. By the way, this whole API is changing in their next release. So, cool. The onload function. The onload function is going to declare any resource arcs that you might have. There's some other things that you could do with it that I'm not going to get into here. And this is basically just setting it up on the Rust side of things. So when it loads, these exports happen. Now all these functions are available. And you can call them as if it's normal Erlang or Elixir functions. So this is prepare, that first function. You'll notice that the arguments are a list. This is a slice in Rust. This is Rust code, by the way, of terms. So terms is describing, it's something from Erlang. And we call decode on it, and you pass it a Rust on the left. You're saying, I want it to decode as a vector, so a list of 64-bit floating point numbers. If it doesn't do it, that question mark at the end will return, and it will return an error. But here we're just setting up the state, so we're setting up this game state struct. It's got some read-write locks on the scores. We're going to wrap that in a resource arc, and then we return OK with the OK resource and encode it, and that will ship it back off to our Elixir code. Update is kind of similar. So now, if you remember from the test, we were passing the ref, and we're passing an atom away score or home score. It's going to decode the resource arc and get back that game state. And then it's also going to decode what we call the incident. I don't actually show this. It's an enum type. And that enum type will do automatic conversion because we annotate it as a unit enum from the atom into that type. We then call state.update, and it will update the state of the game. Get scores is going to do a similar thing, but it's just going to pull them out, make sure they're returned as integers, and send them back to Elixir. So this is the code that we just saw, that it takes the game state and it calls update with the incident. It's then going to pattern match, which is very similar to a case, nearly identical actually. And it's going to pattern match on the incident. The cool thing that Rust can do that Elixir can't is if I were to say have home score and I didn't take care of away score, it would be a compilation error and tell me that I didn't handle all of the cases. But this is just updating the state, adding one to it. And then predict, our fake model, it sums up all the numbers that we passed in the prepare, and then adds the home score, away score, multiplies by a multiplier because I said so, and then divides by 1,000, then we get some probability. So if you can imagine, this is like a contrived example of how we send state into Rust. We have our machine learning code that's actually doing all the feature engineering. We're sending state updates to it, and then periodically we're calling predict, and we're getting out what I said as a probability, but in the case of SimpleBet, probability distribution. And then just one more time, just because it was a little bit back. So again, we call prepare. All it's doing is passing that ref. Each time it knows to pull that resource arc out, and then we're still able to call functions to get more data out of that resource arc. So Simple AI. Simple AI was SimpleBet's Rust machine learning framework. 150,000 lines of Rust. And you can see the little purple on the right, so there's a little bit of Elixir wrapper. I'd like someone to challenge me that they've written a bigger application level NIF. It's a bad idea, don't do it. So the components of this library, so we had Core AI, which is a machine learning framework. We were building all of the structure that you would expect in a machine learning framework like in Python or in R. Simple math, which are machine learning algorithms like k-means clustering, regression algorithms, Bayesian algorithms. Then we had Simple AI, which was the wrapper that sort of consumed some of these other things and made that interface. And then Baseball, which were the baseball specific model and state data updating functions. So this is the process for building a model. A data scientist would iterate on a model until it was perfect. They would then write Markdown to describe the model. So they'd annotate every feature, every filter, the prediction function. They'd also describe anything else, nuances of the model that it might need, clustering algorithms, et cetera. And then they'd also describe in plain English what each feature of the model, what it did. Now we would start to write Rust, so throw it over the wall. We'd implement that model in Rust, given all of that information. And we'd write integration tests and unit tests to verify that it was correct. And then once we implemented the model, we'd tag it for release, bump the version of AI, Simple AI, integrate it into that consuming platform application. And then that consuming platform application usually need to change a ton of code to make sure it's passing data incorrectly. Okay, so the challenges with this, a lot. One, the model execution time. So when you run a NIF, you're competing with the scheduler. The NIF does not consume reductions. And there's ways around this. So there's a feature called dirty NIFs, which moves the NIFs onto its own thread. We played around with that. What we got the best execution out of was when we were yielding back to and from the scheduler. Roughly, we track how much time we were taking inside the NIF. And then if we're getting close to a millisecond, we'd yield back and then yield back into the NIF. Found that transferring data from Elixir into Rust was very slow. We were passing all the data we needed into the NIF and that prepare, but it was this constant battle because just the transfer could actually consume that whole millisecond and mess with the scheduler. And ultimately, we pushed way too much code into the Rust NIF. Frank was giving a talk earlier and talking about nerves and battling C and Erlang, and there was a lot of contention on what belonged on which side, and it always felt like there was kind of duplicating effort on both sides of this thing. There's also some problems at the time with encoding data from other crates. So I mentioned before we had split our model code separately from the NIF code. And so encoding data into types from other crates at the time was very difficult. I had posted an issue at this at the time, and then someone responded by making the Surday Rustler crate, which was really cool. Haven't used it yet, but I assume it makes it a lot easier to deal with. And then the other problem was argument error, which is everyone's favorite way to find out that you have a bug in a megabyte-sized data payload that you have, and it's up to you to find out which float should actually be an integer. That's actually when I started contributing to Rustler, added some very small error handling features to say hey, this key on this struct name is failing. All right, so this is a success. I said in the beginning of the talk that we had an app that we launched for a private beta for the World Series and the playoffs, and believe it or not, this actually worked really well. So we were able to get a product out. It got very good response. It generated odds as the game was happening in real time. And we were able to prove that what we're doing was possible, and now we just had to bring it to market. So Naturally is very excited about this. I tricked Desmond and Chris to let me talk about it on Elixir Talk, evangelizing the Dream Stack. But maybe, this whole Rust thing, maybe we're trying to go too fast. So what if we were building a Ferrari when all we really needed was a go-kart? So the success that we had with this NIF was really great, and it was awesome. We were very excited that we were able to build this thing. It was very intellectually captivating, and having that desire, I want to work on the cutting edge in Rust, and that felt really, it was just fun. But this implementation was very expensive, very hard to add features to. We were wondering why it was so hard to document models. Like, it's just a feature. And why has no one else solved this problem? The reason is no one does that. So every time we wrote a model, we had to write it twice. And this was just a extremely expensive process. And it was all done because we jumped for the thing that was the fastest implementation first, as opposed to the simplest implementation. So survivorship bias is the logical error of concentrating on the people or things that made it some past selection process and overlooking those that did not, typically because of their lack of visibility. So again, that Rust approach we took worked, despite the issues that it had. And we easily could have kept going down this path, and we could be investing more and more resources into this Rust NIF. It was correct and it was technically correct, but that's kind of like, the worst way to validate that. And so, you always have to challenge, what are our core assumptions about the product we're building? So that's when we start to look at okay, organizationally, how are we set up? So we have, a team of data scientists who are doing research, and then we have to document this whole expensive process. We throw it over the wall, and then the machine learning team builds the model that goes to production. So 2 implementations for effectively the same thing. So Conway's law, I think it's a different Conway than Conway's Game of Life. Conway's law states that an organization who designs a system will produce a design whose structure is a copy of that organization's communication structure. So the team designing the models, backtesting and stress testing them were a different team than the one that was building the production model. And they were written in different languages, Python for research and Rust for production. So what we did has a ridiculous name, and it's called the inverse Conway maneuver. So we took our strongest data scientists who had the most software expertise, and we made them into the machine learning engineers. While Rust was super fast, we really only needed a go-kart. So we started using Python for the entire chain and started investing more into the Python tooling and started to make use of industry standard algorithms and frameworks and all the latest and greatest that the community was supporting. So when you take your organizational structure and you modify it to reflect the architectural structure that you're looking for, that's this inverse Conway maneuver. And the real problem that we were solving was that the flow of this machine learning engineering team, it was constrained by this high bandwidth communication that needed to happen between these 2 teams. We wondered why it was so hard to document these models, but we never really questioned why we needed to document them in the first place. So what we ended up doing is, that team, we invested in that, and the data science research team now became this machine learning engineering team with a really strong focus on, from research all the way to production, you own the tool chain. And rather than having this split between Elixir and Rust as a NIF, you just put the service boundary and go over the network. So again, what if we were successful despite the obstacles we created? So now that we made this change, we still have Elixir and it's doing all this coordination, but now rather than having to wait and to redeploy every single time on the Elixir side that we want to make a model update, now we just have to independently deploy this Python service, and we can deploy new changes, new upgrades to models independently. And these teams, as long as they adhere to the same API, they don't have to spend so much time communicating inter-team. So you want to keep the intra-team communication bandwidth high, but the inter-team communication bandwidth low. So I've talked to a lot of organizations who are also trying to figure out how do we get our data scientists models into production. And at SimpleBet, we've learned a lot of lessons about that. One of the things that I didn't really talk about so much is that data engineering always needs to come first. The availability of data is core to a data system. But also, it's really important that when you're doing machine learning, that those people who are designing the models are the ones who are deploying them. And that value stream always needs to be there, and there can't be any friction. So don't go against the grain. Choose the boring technology and lean on the community. And remember to be cognizant of Conway's Law and how that might be affecting your technology decisions. So just to end, these are some amazing books that have informed a lot of my thinking in the last 6 months. Team Topologies especially will talk about Conway's Law. Accelerate is just a great book about getting into the DevOps philosophy. And then this is the driest but probably most important book that you'll read as a product-focused person, which is an economic approach to product development. And here's some other resources, and thank you.
We have some time to do 2 questions, please. Okay. Someone?
Curious just what the performance difference was between the Rust and the Python. I'm curious about what the performance difference actually was when you removed the Rust and went to Python.
So when we were in Rust, I think we were on the order of individual models could run on the order of microseconds. But we were running them in aggregate. So, the whole aggregate of running predict on all those models, maybe it's like single-digit milliseconds. Now we're on the order of like several dozen milliseconds. So still within our performance budget, fast enough.
Anyone else? I have one question. How safe was that part of that communication between the Elixir and Rust that you implemented?
So there's a lot of facilities for doing encoding and decoding, and Rustler makes it pretty easy for you to catch decoding errors coming in and respond to them however you want. You can have it throw an error. You can have it return error tuple with extra information. So safe? Yeah, very safe. Like, it's not going to crash the beam. It's just going to return an error or throw an error.
Thank you, David.